Hello, I'm just loving this, proving Fibonacci properties using matrix. So in this last few videos in the Fibonacci sequence, what I've done is we basically found out the matrix representation for Fibonacci numbers and then used that to find a sum of Fibonacci numbers from base I to base n. Yeah, and we are basically using the same principle, but this time to find the sum of odd Fibonacci numbers with base odd number and Fibonacci numbers with base even number, right? Now I think you if you have watched the previous video, I have proved that if we multiply this matrix n times, that means raised to the power of n, what we get is n plus 1 Fibonacci number, n Fibonacci number, n Fibonacci number, and n minus 1 Fibonacci number, right? And we basically exploited the same property to find the sum of Fibonacci numbers. Now, in this video, we are again using the same thing to find the sum of odd and even Fibonacci numbers. Now, how will I do is, I will try to evaluate this sum from for the first one to prove the first theorem over here, the first one. I will just evaluate this sum from I equals to 0 to n of 1 1 1 0 to the power, let's say, 2i. Yeah, now what this does is, we know that from this theorem, we know that from this property that I proved in previous video, this will just be same as sum from I equals to 0 to n of 2n Fibonacci number, 2n Fibonacci number, 2n minus 1 Fibonacci number, 2n plus 1 Fibonacci number, right? And this will just be, we know that in matrix that its corresponding elements will be added, right? So this will just be the same as sum from I equals to 0 to n of f2n plus 1, sum from I equals to 0 to n of f2n, sum from I equals to 0 to n of f2n, and sum from I equals to 0 to n of f2n minus 1. Now, if I am able to evaluate this some way using geometric sequence or something like that, and if I compare this second element in this matrix, I will get my required answer from here, right? And if I compare my first thing in the matrix, I will also get the first answer and second answer. Both of them can be got from, we can get from the same arithmetic. I mean this from this same calculation that we are doing over here. Yeah. So now let's try to see how we can do that, how we can evaluate this sum over here. Now you might have noticed that over here there is some index error. Like, what does Fibonacci number base minus 1 mean, right? I will show you later on like how to extend the Fibonacci number, and yeah, this will make sense at the end. But for now, let's try to see how we evaluate this sum. Okay, so we want to find this sum, right? Sum from I equals to 0 to n of 1 1 1 0 to the power 2i, right? Now what I will try to do is, I will use the geometric sequence. We know that in a geometric sequence, if we have sum from n is equals to j, let's say I is equals to 0 to n of a, and then r to the power I. Yeah, in this case, if this goes from 1, we write r to I to the power a, r to the power I minus 1, but since this goes from 0, there's no need to write minus 1 over here. So we know that this evaluates to a r to the power number of terms is n plus 1 over here minus 1 by r minus 1 over here, right? We'll use the same formula, and yeah, magically that works. I don't think that's magic, because in the derivation of this formula we don't really specify what a and r are, right? We don't really specify them as numbers, and that's how it's derived. So that's supposed to work over here, right? And it does. Now our first term is basically our a is to the power 2 into 0. This is our first term, a, and then r is just 1110 square. This is the r, and number of terms. Number of terms is n plus 1 minus, there is supposed to be 1, and in matrix 1 is just the identity matrix, right? I can use eraser, I guess. Yeah, 1 is just identity matrix in matrix form, and then divide by r is 1110 square minus 1, right? Now we know that anything to the power 0 is just 1, and in matrix form 1 is basically 1001. But again, if that unit matrix multiplied this thing, again that will be same. So this is basically as same as nothing, right? So I will not basically write that thing, this unit matrix over here, this thing that we will get. So this one is just I, which is 1001, but since that will multiply the other one to give the same thing, so we can just ignore that, right? And after that, what we can do is, now we'll start evaluate this. Over here, this is 1110 to the power 2n plus 2 minus 1001, and divide by, if you take the square of this, you will get 2111 minus 8. This one is just unit matrix, I forgot that, minus, I don't think this is called unit matrix, I'm sorry, this is called identity matrix. I'm sorry, this is identity matrix, 1001, right? Now we know that from again the same formula that we had in the beginning. If you use this formula, we can find the nth power of this matrix, right? Nth power of this matrix over here, and that will be f2n plus 3, f2n plus 2, f2n plus 2, f2n plus 1 minus 1001 divided by this thing over here will just be 1110, right? Now if it goes, now we have to take inverse of that thing, f2n plus 3 minus 1, f2n plus 2, f2n plus 2, f2n plus 1 minus 1 multiplied by its inverse, right? We know how to find inverse of matrix, right? Inverse of A, B, C, D will just be determinant AD minus BC, and then DA minus C minus B, right? So we will use this thing. I guess you know that, so let me erase that one. Okay. Now since you know that, now we can find that over here it will be the same thing. It will be the same thing. Yeah. Now and over here, this will be 0 minus 1 minus 1, and 0 1 minus 1 minus 1, right? And now if the minus 1 multiplies them, what happens is, if the minus 1 multiplies them, 0 will be 0, this minus sign will be removed from there, and this will have minus sign, right? Now there will be 1 and minus 1. Now after this, let's multiply again. We will get f of 2n plus 2 over here, and f of 2n plus 3 minus 1, and then and then I guess it will be minus over here. F of 2n, this multiplies with this thing, right? So minus f of 2n plus 2. Now this multiplies to get f of 2n plus 1 minus 1. Now this 2 and this 2. F of 2n plus 2, f of 2n plus 1 minus 1, 1 minus 1. So f of 2n plus 2 minus f of 2n plus 1 plus 1. Right? Yeah. Now let's try to see what this evaluates to. F of 2n plus 2. Now that will just be f of 2n plus 1 minus 1. F of 2n plus 1 minus 1. right? And this is f of 2n plus 1. Now we know that this thing we're also supposed to be these forms, right? Yeah. So let me just erase this a lot of lines that just make it look messy, they just make it look untidy. We don't get the feeling that we are doing something really pure and pristine. That's math. Yeah, and this is, I think I have to avoid being this messy, because yeah, now it looks good. Yeah, now it looks like we are doing really good stuff, since there are no miss and there's not really any miss. Yeah, now it looks good, right? Yeah. Okay, now we know that this expression over here is actually equals to this sum, right? So this expression is the same thing that we manipulate over here. So this final result should also be equals to, this should be equals to sum from I equals to 0 to n of f, what was that, 2n plus 1, f 2n plus 1. This should be sum from I equals to 0 to n of f 2n, sum from I equals to 0 to n of f 2n, sum from I equals to 0 to n of f 2. Oh yes, I'm sorry, these are supposed to be I. Okay, 2i 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 minus 1, right? Now from here, if you compare the first with first element, we get that sum from I equals to 0 to n of f2i plus 1 is equals to f2n plus 2, right? If you want to check that, you can take n as, let's say, 3. If you take n as 3, sum of f of 1 plus sum of f of 3, sum of f of 5, sum of f of 7, this is too large. Just take n as 2. No, n as 1, let's say. Just take n as 1. Just take n as 1. So this sum of these two should be equals to f of 4, right? This is just 1. This is just 2, right? 1, 1, 2, yeah. And this is 3, right? Yeah, 3 equals 3. See, that works. Now let's go to the other. Let's get some other formulas as well. Okay, and one of the other formulas that we can get over here is from the second expression is sum from I equals to 0 to n of f of 2i, from which is over here, that is f of 2n plus 1 minus 1. Yeah. Now how to make sense of this result? Now let's try to see how to make sense of this result, because there's an index that's not valid, right? Sum from 0 to n of f of 2i minus 1. Over here we can separate this index f of minus 1 plus sum from I equals to 1 to n of f of 2i minus 1, right? Now we know that in Fibonacci sequence, f of 0 is 0, f of 1 is 1, f of 2 is 2, sorry, this is just 1, f of 3 is 1 plus 1, 2, f of 4 is 2 plus 1, 3, right? Now f of minus 1 should be a number such that number plus 0 is 1, right? This plus this should be 1, so that's why this number would of course be 1, right? So that 1 plus 0 would be 1. Minus 2, there should be a number over here so that the number and 1 would sum to 0, so f of minus 2 is minus 1. So this is how you extend the Fibonacci numbers. That's why f of minus 1 is just 1, right? This is 1 plus. Now we know that I can write this as sum from I equals to 0 to n minus 1 of f of 2i plus 1, right? And now we know how to evaluate this sum. That will just from here, that will just be f of 2 times n minus 1 plus 2. So that is 1 plus f of 2n, which is exactly what is over here. See? So we have made this science of this one as well. And yeah, we have achieved our goal finally. We have achieved our goal using just a matrix. And yeah, you see that this matrix is really powerful. This can prove a lot of theorems. Yeah, I have already proved 3 of them, and 2 of them in the same video, in just the same manipulation. So yeah, this was the proof. If you want to just review it, we first use the formula to get the first kind of sum expression. Again, we manipulate it in some different way to get another sum expression which involved n Fibonacci numbers, and then we compared them, and by comparing we got the formulas for sum. So, we also extended Fibonacci numbers to make sense of the result that we got over here, and we made sense of that. So that it is. Hope you enjoyed the video. Thanks for watching. Also check out the other videos on this Fibonacci sequence series. I really love them and hope you would too. Thanks for watching. Look forward to seeing you in the upcoming video. We are just dealing with matrix and Fibonacci for a few days, around per week, and then again we'll come. Of course, we'll come back to integrals. Yeah.